Going, getting into this atomic orbitals. Super exciting stuff. There we go. That's better. I love this stuff. This is really cool. When I teach general chemistry and we talk about the orbitals, I always love telling the students, if you have me in PChem, we're gonna come back and we're gonna see this stuff in full detail. So here we go. Okay, so what's probably familiar to you are the sub shells, SPD, F, etc. Okay, corresponding to L is equal to 0, L is equal to 1, L is equal to 2, L is equal to 3, and then so forth. Okay. So maybe something you might not be familiar with. So S, if you're ever curious why S, P, D, and F, S equals sharp, P equals principal, D equals, I can't write, diffuse, and F equals fine. And those are all references to the types of spectra that are observed from those various subshells: sharp, principal, diffuse, and fine. We don't really use that language so much anymore. It's kind of an older language, but that's where the SPDF letters come from. And now, because that's the end of the periodic table right there, after the F subshell, it just goes in alphabetical order: G, H, I, etc. Okay. So maybe what you're less familiar with is this notion of shells. Okay. So shells are in reference to the principal quantum number n. So when n is equal to 1, we call that the K shell. When n is equal to 2, we call it the L shell, and then M, N, and so forth. Okay? So if we look at our old familiar energy level diagram, and I'll note that this diagram is for hydrogen only, because for hydrogen only, the subshells are degenerate. Okay? Degenerate for hydrogen only. Okay? And that's because it only has one electron. So as we shall see, when we start having multi-electron atoms, the subshell energy levels split due to electron-electron interaction. But for hydrogen and hydrogen only, okay, here you can see we've got the K shell corresponding to n is equal to 1, okay, and there's only one degenerate level in that K shell for hydrogen. As we go up to the L shell, okay, n is equal to 2, you can see that we've got 3 degenerate subshell states, right, the p orbitals, and 1 degenerate s shell state, subshell, excuse me, okay? And then so on and so forth, right? We get the L shell corresponding to n is equal to 3. And in that level, we have the 5 degenerate states from the, or really I shouldn't even say 5, it's 5 plus 3 plus 1. It's really 9 degenerate states, right? Corresponding to the S, P, and D subshells, okay? So hopefully this is somewhat familiar to you, but we use this nomenclature quite a bit in spectroscopy, this KLMN shell nomenclature. Okay, so be familiar with it. Okay, we're gonna go one by one talking about all of the various orbitals. So s orbitals, okay, so psi 1, 0, 0. So I've already demonstrated how we constructed this wave function, and a little tiny mistake there, that should be z cubed, right? You can see my Mathematica file there next to me, okay? And so again, remember the 1, 0, 0, that's n is 1, L is 0, and L is 0, okay? So a few qualitative points of discussion. The closer an electron is to the nucleus, the lower is its potential energy. And one reason for that is because here we note that the high degree of curvature, if you recall from way back in chapter 7, A large curvature in our wave function corresponds to a large kinetic energy through second derivative analysis, okay? So that means up in this region, the closer the electron is to the nucleus, the higher is its kinetic energy, okay? And so as it gets farther away, this region of low curvature indicates that its kinetic energy is becoming very low, but its potential energy is becoming very high, okay? And our s orbital wave function is spread out, so it's smeared out, just like you can see with this exponential decay, right? And it's spherically symmetrical. All right, so this is just looking at the radial component. I know I've plotted the whole psi 100, but on this type of graph, it's only going to show us the radial component. But if we look at a three-dimensional representation, we can see that exponential decay given as this shaded area, right? So you can see here where this dark color, it's much darker at the origin, so that indicates higher probability at the origin. And as we move further away, we have decaying probability, okay? And that's spherically symmetrical. So hopefully what you're familiar with, if we look at the 2s orbital, and so let's just back up really quick and look at the radial graph. I've got that right here, okay? So remember, there was one node on the 2s orbital, and we can see that on this spherical plot right there, okay? And so what ends up happening then is at the first region, we have this exponential decay, okay? But then in the second region, so I'll kind of try to represent that with my red color, looking something like that. But in the second region, it's not so much of an exponential decay as it's some function that hits a maximum and then decays again. And if I'll go back to that radial profile and show you that, you can see that right here, okay, where there's this decaying region. And then even though this goes to negative values, oh no, my mouse battery is low. I hope it doesn't run out during this recording. So this region right here, if we were to plot that region as psi squared, that's going to give us that maximum that I drew right here, okay? So I like to kind of call these the onion layers. And hopefully, as you remember, when we go to 3s and 4s and 5s, we get more and more of these onion layers, okay? So let's keep talking about s orbitals. And now what I want to get into is their what's called the radial distribution, PR, okay? So we recall that when we take the square modulus, this gives me the probability of finding the particles somewhere. Okay? And so if you recall now, if I put this whole thing together, right, as it turns out, I'm not going to show this derivation, but for all spherically symmetrical wave functions, we can create this probability distribution by going 4 pi r squared times psi squared. So where does all that stuff come from? Well, I'll remind you, d tau, right, when we carry out this operation right here, okay, and then again, noting that psi 100 equals r of r 10, and then y of theta phi 00, right? Well, when we put all that together, okay, remember that the YLM, so I'm only going to draw that portion here on the integral, 0 to pi and then 0 to 2 pi of the YL ML, and then square modulus, right, squared, and then remember that we have this sine theta d phi, okay? And then we also have that radial component, 10 of r times r squared dr, from 0 to infinity. So we recognize that all of this is normalized in the sense that it's all equal to 1, okay? So what ends up happening here, we're going to define this function p of r dr as, and I'm going to drop the integral here, of just r of r squared dr. And then now all of this stuff is already normalized to 1. Okay? So the dr and the dr cancel, and we get that PR equals R times R squared. And this ends up being the case for all spherically symmetrical, or for all non-spherically symmetrical wave functions. And buried within the proof that I'm not going to go to in full detail, for all spherically symmetrical wave functions, it's an additional factor of 4 pi. Okay? And I should say that equals 4 pi R squared times R of R squared. Because in this sense, the spherically harmonic wave function is normalized to 1. And again, we have to include that additional 4 pi factor for spherically symmetrical wave functions. So what does this graph look like? Let's see here. So here I've got it plotted out, okay? And then remember that's z cubed, okay? And so I've also got that on my Mathematica file right here. And I've got that on a manipulate, so I can change the charge. Okay, so remember, z equals +1 for hydrogen. And so when we look at this radial distribution for the 1s orbital, so this is 1s, this is really cool. Check it out. The maximum, if we look at where that is, and you trace it down, it's right around 50 picometers. Okay? Can we get a more exact value of that? Well, we can. And so how would we do that? Well, if I want to find the maximum, I would say take d p of r dr and set it equal to 0 and solve for r that satisfies that equation. Well, I did that in my Mathematica right here, okay? So you can see I've got, I'm calling it most probable radius, and I'm solving. Here is the derivative of my psi 100, and then I've got 4 pi r squared psi squared, okay? So I'm doing the proper radial distribution function that I put together right here, okay? And I've set that equal to 0, and I'm solving for r. And I've also, on my code right here, that number 1 that I've highlighted, that z is equal to 1. And check it out. We get A for the Bohr radius. Very cool. So that peak is, in fact, 52.9 picometers. And the most probable radius for finding the 1s electron and hydrogen is the Bohr radius. Very cool stuff, okay? So now what happens when we change the charge, the internuclear charge? What effect does that have? So we're still just looking at psi 100, so 1s. But suppose we change the charge to z plus 2, okay? Check out what happens. Ooh, look, it moved closer to the nucleus. And if I go z plus 3, it moves even closer to the nucleus. And if I keep going with this, right, +4, +5, +6, okay, you can see that the function is getting more compressed because it has to be the same area. All we've done is change the z. So for the same area, it has to become more compressed and taller. But that changing that internuclear charge to higher values has the effect of sucking the electron in even closer, which is what we remember from our general chemistry days, okay? And what's also really cool on solving where that maximum is occurring, so here on my little Mathematica problem, I can just make the z equal to 2 right there. That's what I just did. And I'll evaluate it. And look, the most probable radius becomes a over 2. And if I go to 3, it becomes a over 3. And if I go to like 7, it becomes a over 7. Okay. So what's going on there is now if you look at all of these calculations, so this is what I just did, right? And so remember, this is still just a 1 electron system, okay? So all we're doing is just adding more protons into the nucleus, right? And so you can see the effect that has by changing the nuclear charge with only 1 electron. It really dramatically sucks the electron in closer to the nucleus. And that's represented by this picture right here. Okay? Very cool stuff. And so even though on the, on the periodic table and in reality, we don't have like carbon 5 plus or boron 4 plus or whatever, but that effect still manifests into the multi-electron atoms. As we increase the charge in the nucleus, it has the effect of bringing the electron closer in, okay, which we can see in this simple model. Very cool stuff, okay? So moving on, let's build up the p orbitals, okay? So there's a lot of stuff going on here. I realize it looks pretty intimidating. So let's put it together piece at a time. So remember, we've got psi2, 1, 0. So n is equal to 2. L is equal to 1. And now specifically, we're going to look at ml equals 0. And I'll remind you that ml equals 0 is special for the z-axis. So by definition, when we look at psi2, 1, 0, we're looking specifically at pz. And we're going to create this pz wave function, psi pz, and specifically we'll define our p orbital as the square modulus psi star psi of psi210. Okay, so let's build that up. So I can separate that into the radial and angular components, r21 and y10. Okay, and so instead of saying 210, we'll just adopt the psi pz nomenclature. And now if we look at our spherical harmonic function and our radial function, then we're just going to smash them together. Literally multiply, the root of 3 over 4 pi cosine theta times this radial function. Okay? And so there's some algebra that's been done. And so I'll also remind you, right, that rho is this 2zr over na. So I'm not going to worry too much about going through the algebra, showing you where this comes from. But basically, it's this function times this function, right? That's how we got it, okay? And then collected like terms. So what's also pretty cool, what I'm going to remind you, the reason why we really like to adopt this pz nomenclature, not only because ml equals 0 is special to the z-axis, but also if you recall, that when we do a Cartesian coordinate transformation, z equals r cosine of theta. So that was one of our coordinate transformations from Cartesian to spherical polar chords. Okay, so this was done algebraically. So there was an algebraic manipulation here to show you that here is this r cosine theta, which I'll highlight, and then there it is right there, and then that just becomes z. And then all of this other stuff that I'll box off in red, or here I'll bubble it off. So this term right here, and then this term right here, those get combined into some new function, f of r. Because if you notice now, these red things that I've bubbled off, they only are a function of r, okay? And so we could write a shorthand notation for our psi pz as literally z times some function in r, which is really cool, okay? And as it turns out, if we were to do psi star psi of pz, we would directly get the pz orbital, which is really cool. And I'm not going to show you my Mathematica graph. You can see that the picture of that is right here. Okay, so where this is my z-axis, and this is showing you that there, if we look at psi squared, of course, we're not necessarily going to get regions of positive and negative, but we label regions of positive and negative, and that will manifest later on as we get into bonding and molecular orbital theory. So we're going to do this in Mathematica. You're going to be able to just literally plot this equation, and it's going to be a p orbital. Really cool. A pz orbital. So how do we do px and py? Well, the situation gets a lot more complicated, okay? And it gets complicated because of our Heisenberg uncertainty in the x and y dimensions, okay? So remember that the commutator Lx, Ly equals I h bar Lz, okay? So the fact that this has a value, right, that it's non-zero, that tells us there's uncertainty amongst the x and y dimensions. So we need a superposition to describe both px and py. So we need two separate superpositions, one for each orbital. And here's how we create that superposition, okay? So we're going to look at the psi21 plus 1, right, where ml equals plus 1, and the psi21 minus 1, here where ml equals minus 1. Okay, and if you follow through our nomenclature, right, that's R21, Y1 plus 1. And I'm going to, that's typically referred to as the P plus wave function, right? Check out the nomenclature. We're literally going to call all this stuff R21, Y1 plus 1, just P plus. Great, it's a wave function, okay? And when we have the psi21 minus 1, that's going to be the R21, Y1 minus 1, and that's going to make the P minus wave function, okay? So each of these are their own wave functions that are suspect to Heisenberg. So we have to make a basis set of them, okay? And again, that's because of the uncertainty that arises in the x and y dimensions. So our basis set becomes psi21 plus or minus 1. And the way that's going to go, this is our the superposition we've created, where these ends, of course, are normalization constants. And we have the superposition of the p plus and the p minus state, which corresponds to ml plus or minus 1. Okay? So when we put that all together, right, we look up the R21 and the Y1 plus or minus 1. And so I'm just showing to you this as the plus or minus, right? So remember, when it's plus up here, that corresponds to minus there. And when it's minus down there, that corresponds to the plus right there. And then, of course, it's the same situation up here, okay? So what's pretty cool about all of this is if you kind of compare that we've got this z over a to the 5 halves, we've got this 1 over pi to the 1 half, and if I back up and show you this, there's that z over a to the 5 halves, and this other collection of constants, okay? With some algebraic manipulation, you can rearrange this equation to be, minus or plus 1 over the root 2, r sine theta, e plus or minus I phi, f of r. And that f of r is the same f of r from right here. And so I'm not going to go through the algebra to prove that, but if you rearrange these equations, you can get it so that f of r is the same as this f of r. And so hopefully you can kind of see where this is going. That's what creates the mathematical rationale for calling this either px or py. We still don't know which one is px or py because we have to apply our superposition. Okay? So moving on. So once again, we remember that psi21 plus 1 is p plus and psi21 minus 1 is p minus. And we have our general form of our basis set. So this, I'm not going to go through this derivation, right? We're just kind of showing you where it comes from. But by definition now, we can make a px wave function by the following superposition. So this is already normalized for you. So that's the normalization constant of the basis set. And that becomes a linear combination of p minus and p plus. And then now we also define the py wave function. So I'm going to remind you these are wave functions. Okay. Wave function. And so now we get this normalization constant, I over root 2. Totally fine that has an I in it because we're going to square it. Okay. And so it's also linear combination of p minus and p plus. And so now we're finally poised to define the px orbital as px star px, where px is this equation. Okay, so you have to square this whole thing so it becomes a quadratic. And then you have to square this whole thing to get py. And because we've now used this superposition, we've gotten around the uncertainty principle between the x and y dimension. And when we finish that off, what we end up with is, and more algebraic manipulation that I'm not going to go through, but we end up getting this function f of r, which are the same for all three orbitals, right? F of r for x is the same function of f of r for y, and it's the same function for f of r of z. But now with algebraic manipulation, okay, recall that my x in polar spherical coordinates is r sine theta cosine of phi, and y in polar spherical coordinates is r sine theta sine phi. And so that creates the px py orbital that we can see right here. Here's the results of the Mathematica simulation that you're going to do. And what's really cool is when you put all three of them together, we can see their x, y, z components, which is very cool. Okay. And also, even though these are the square, right? These are values squared. But because we have these imaginary numbers in these functions, we get negative regions, which is also kind of cool. Okay. And there's going to be physical significance to those negative regions. So I'll point out that, right, if you look at, there's the origin, and there's positive values, and there's negative values, right? So that's what gives us this plus minus region, okay? Because we have eyes in our situation. All right, so moving on. So I'm just going to very quickly describe the d orbitals because it's the same situation that's going to manifest, okay? So dz squared, right, the z component, special for ml equals 0, we define as psi32 0, which is going to be made up of r32 and y2 0. And because there's no uncertainty situation with the z-axis, specifically the 3dz orbital will now be defined as psi320 star psi320. Brilliant. Then we'll have the dz squared orbital, which I'll show you a picture of here soon. So now, so remember, there's because L is equal to 2, there's 5 ml states, -2, -1, 0, +1, and +2. So we've taken care of the ml equal to 0, right? That's our z squared axis. So now we have 4 other ml states to consider, and all 4 of those ml states span either the y-z axis or the xz, or I should say plane, or the xy plane. And once again, because we're throwing all of our lot into the z-axis, we now have uncertainty situations to deal with for all 4 of these other ml numbers, -2, -1, +1, and +2. So let's do it, okay? So first, if we look at the +1, -1 state, we can make the d +1 and the d -1, just like we did with p, right? Where that's going to go, r32 y2 +1, that makes the d +1 state. And then the r32 y2 -1, that makes the d -1 state. A superposition is then created and then normalized. I'm not going to hold us responsible for doing that. I'm just going to give you the result directly. So the superposition now for the dyz wave function becomes 1 over I root 2 and d plus d minus. And then if we take the square modulus of that, we get the 3dyz orbital. And similarly, if we use another superposition, so it has a slightly different normalization constant and different permutation, 1 over root 2, d +1 minus d -1, that creates our superposition for the dzx. And if we take the square modulus of the dzx, we get the 3dzx orbital. Okay, great. So continuing along, so now if we look at the +2 -2 ml states, right? So ml plus or minus 2. So we've got the R32Y2 plus 2, and we'll call that the D plus 2. And we've got the R32Y2 minus 2. We'll call that the D minus 2. Fantastic. And in the same way, we get superpositions of either that will then correspond to the 3dx squared minus y squared or the 3dxy. And that comes, again, from this algebraic manipulation, f of r. So it's important to note this function f of r now does not equal, so for the d, does not equal the f of r function for p orbitals, right? But within the same block, or I should say the same subshell, within the same d subshell, that f of r function is the same for all of these. And so you can see through algebraic manipulation where those labels come from. The dxy is literally x times y times this function in r. Or, for example, the dx squared minus y squared is not quite identical to that, but it's close. It's 1/2 times the quantity x squared minus y squared times f of r. And the dz squared is a little funky, right? It's not like a pure z squared times f of r, but all the same, it still has that z squared, okay? So here's the picture of all those d orbitals that you all know and love from your Gen Chem days, okay? Oh, this one I just noticed says dx squared, but that is dz squared. That's a mistake in the textbook, haha. But what we're gonna do, we're gonna take this and put it in Mathematica. And what I always find really cool, like, as an undergrad, I always wanted to see all of these orbitals like put together on the same graph. And no one ever does that in textbooks for some reason. But here, we can easily do that in Mathematica. And that's what it looks like when we smash all 5 of those d orbitals together. And what I think is really cool when I think about this kind of shape, if I imagine like a transition metal, for example, that has a full d block, you know, we often, like when we draw pictures of those atoms, we just kind of draw them as little spheres, right? Like maybe if I had, you know, zinc atoms or something like that, right? I'd just have a bunch of neighboring zinc atoms as spheres, and you know, in an atomic lattice, right? They're all just going to be lined up. Well, when you look at all these orbitals together here, to me, I think a sphere is a pretty good approximation of this shape. It's crazy. It's got all these lobes sticking out. But as a gross approximation, if this were a full D block, right, everything is completely symmetrical about that point of origin, which is really neat, okay? So let's see here. So the last thing, where are we going with this stuff? Yes, so I've been talking for quite a while, so I'll just try to wrap it up. If we now compare all of these different radial distributions, 1s, 2p, 2s, we can see the trend, and hopefully you remember this from Chem 109. And this is where we're going next is, you know, for the 1 electron atoms, or excuse me, what happens when now we have multi-electron atoms? What happens to this model? I also have a cool little Mathematica file I downloaded from the internet. It's called the Wolfram's Demonstration Project. So this is really cool. So they've got this whole manipulate feature, and they're plotting the radial wave function and the radial distribution wave function, and you can select through the different n and the different l's. So if we look at, so I'm going to go back now in my own Mathematica, right? When I made z is equal to 1 for 1s, that's the same function. Okay, this blue line here, if you remember our nomenclature, that gives us the expectation value, which if you remember for hydrogen 1s, that's about 72 or so picometers. So even though the most probable value is at the peak, the expectation value is right there. And it actually has to do with areas under the curve, right? The area under the curve to the left of that expectation value and the area under the curve to the right of that expectation value. Very cool. So now when I go up to n is equal to 2, this is a really cool model. So it goes to 2s. And so here you can see the radial profile for 2s. And then now you can also see those onion shells I was talking about, right? Those onion layers. So there's a node. The expectation value for 2s is, of course, out in that outermost lobe or layer, right? If we look at 3s, we get a similar situation. Okay, so there's the radial, and it shows 2 nodes. And now what's kind of cool is the expectation value for 3s is becoming much closer to the most probable value for that third lobe. And again, that just has to do with the areas under the curves. Okay. And then 4s, we see something similar, okay, which is very cool. But now what I can do is I can go back to this 2s, but I can now make it a 2p. All right. And so no more nodes. You can see that's where the expectation value is. I can look at 3p, and I see a similar situation. I can look at 3d, and right, remember, 3d won't have any radial nodes, so we see that there. And then finally, I could look at 4d, or I could even look at 4f, okay? And you would expect 4f to look really complicated, but it's not at all. And again, that's because of the way that radial nodes go as n minus 1 minus l. Okay, that's a pretty long lecture. Again, I know this was big stuff, so we should all take our time to digest this material. Okay, folks,